When you design security for traditional IT environments, your primary concerns are usually data confidentiality, application availability, and user access control. When you design security for operational technology, OT, and critical infrastructure, the priorities shift dramatically. In OT environments, you are protecting power generation systems, water treatment facilities, manufacturing plants, transport systems, energy distribution networks. Here, availability and safety often outweigh confidentiality. A breach in IT may result in data loss. A breach in OT may result in physical damage, environmental harm, or human safety risk. As an enterprise security architect, you must recognize that OT is not simply another network segment. It is a different operational domain with different priorities, constraints, and risk. Your architecture must reflect that reality. IT systems are designed for data processing, business applications, email and collaboration, cloud platforms, DevOps pipelines. OT systems are designed for monitoring physical processes, controlling machinery, managing industrial equipment, real-time operational stability. IT prioritizes confidentiality and data integrity. OT prioritizes availability and safety. In IT, patching systems regularly is expected. In OT, patching may require production shutdown. In IT, latency is manageable. In OT, milliseconds may matter. When IT and OT networks converge without architectural discipline, risk increases dramatically. For example, if corporate IT credentials are compromised and network boundaries are weak, attackers may pivot into OT environments. This convergence is one of the most dangerous architectural weaknesses in critical infrastructure sectors. As an architect, you must design explicit trust boundaries between IT and OT. Industrial control systems, ICS, introduce unique risks. These systems may include programmable logic controllers, PLCs, supervisory control and data acquisition SCADA systems, distributed control systems, DCS, human-machine interfaces, HMIs. ICS environments often contain legacy systems, unsupported operating systems, limited encryption capability, weak authentication mechanisms. These limitations are not due to negligence. They are due to operational constraints and long equipment life cycles. Risks in OT environments include unauthorized control manipulation, command injection, lateral movement from IT networks, supply chain compromise, remote access exploitation. Unlike IT breaches, OT compromises may lead to equipment damage, operational shutdown, environmental incidents, public safety risks. Your architecture must prioritize containment and monitoring without disrupting operational stability. Segmentation is the foundation of OT security architecture. You must design layered network zones that clearly separate corporate IT networks. Demilitarized zones, DMZs, OT control networks, safety systems. A well-designed segmentation model prevents direct communication between IT and OT unless explicitly required. For example, corporate users should not directly access PLC networks. Instead, access may be mediated through controlled jump servers, monitored gateways, or segmented access zones. Segmentation should enforce strict firewall policies, one-way data flows where possible, limited remote access, explicit logging of cross-boundary traffic. Micro-segmentation within OT can further reduce risk. If one control system is compromised, segmentation prevents cascade impact across the entire plant. Segmentation reduces blast radius. In critical infrastructure, blast radius equals operational impact. Architectural discipline in segmentation directly protects safety and continuity. Unlike IT systems, you cannot always deploy aggressive endpoint agents within OT environments. Monitoring must often rely on passive network traffic analysis, industrial protocol inspection, log aggregation from control systems, behavioral anomaly detection. Your architecture must support visibility without destabilizing operations. For example, deploying intrusive security tools on legacy PLCs may not be feasible. Instead, you may deploy network-based detection systems that monitor traffic patterns. Security operations architecture must extend into OT environments carefully. Detection capability must integrate with SOC workflows without overwhelming analysts. OT alerts must be contextualized. False positives in OT can cause unnecessary operational intervention. Architectural maturity ensures visibility without volatility. In sectors such as energy, utilities, and transport, regulatory expectations are rising. In Australia, frameworks such as the Security of Critical Infrastructure SOCI Act place obligations on operators of essential services. Compliance drivers may include risk management program requirements, incident reporting obligations, asset identification and criticality mapping, supply chain assurance, mandatory security controls. Energy sector standards may impose network segregation mandates, access control requirements, monitoring and reporting standards, periodic security assessments. Your architecture must embed compliance requirements structurally. Compliance should not be an afterthought. For example, if SOCI requires incident reporting within specific timeframes, your logging and detection architecture must support rapid investigation and evidence gathering. If regulations require asset inventory, your architecture must integrate asset management systems with risk assessment processes. Compliance becomes sustainable when architected, not when audited reactively. Digital transformation often requires IT-OT convergence. Examples include centralized monitoring dashboards, cloud analytics on operational data, remote maintenance capabilities, predictive maintenance systems. Convergence introduces efficiency but increases exposure. You must design secure convergence models that include segmented integration gateways, role-based remote access, multi-factor authentication for OT access, encrypted communication channels, continuous monitoring of convergence points. For example, if operational telemetry is sent to cloud analytics platforms, you must ensure data flows are controlled. Access to analytics platforms is restricted. Data integrity is verified. Unauthorized command injection is impossible. Convergence should not create direct bidirectional trust. It should create controlled, observable integration points. Secure convergence balances innovation and safety. Identity principles apply in OT, but implementation differs. You must ensure unique user identities, no shared administrator accounts, privileged access monitoring, controlled vendor access, time-bound remote access. Vendor access is particularly sensitive. Third-party engineers often require remote access for maintenance. Without proper control, vendor access can become an attack vector. Your architecture must enforce strong authentication, segmented access zones, logging of vendor sessions, session termination policies. Identity governance extends into OT. Even if technology constraints limit some capabilities, architectural intent must remain strong. In IT environments, incident response often focuses on restoring systems and patching vulnerabilities. In OT environments, response must prioritize safety, operational continuity, controlled shutdown procedures, communication with regulatory authorities. Your architecture must define isolation procedures for compromised segments, emergency response playbooks, communication pathways, escalation processes. Containment speed determines operational impact. Architecture determines containment feasibility. When presenting OT security architecture to executives, focus on operational continuity, regulatory compliance, public safety assurance, reputational protection, resilience under cyber threat. Avoid deep technical protocol discussions. Frame the conversation around risk reduction, business continuity, regulatory readiness, strategic investment. Executives must understand that OT security is not optional. It is existent. Ask yours. Are IT and OT environments clearly segmented? Is there visibility into industrial control traffic? Are vendor access pathways tightly governed? Are compliance obligations embedded into architecture? Is convergence controlled or ad hoc? Critical infrastructure cannot tolerate architectural ambiguity. Security architecture in OT must be deliberate, layered, and resilience focused. The stakes are higher. The tolerance for failure is lower. You must architect accordingly. If this lecture helped you understand the complexities of securing OT and critical infrastructure environments, make sure you subscribe to this series. In the next lecture, you will explore governance, risk, and compliance architecture and how to build assurable enterprise security. Like this video if you found it valuable. Comment below. And tell me, does your organization treat OT security as a specialized architectural domain or just an extension of IT? Your journey toward mastering enterprise security architecture continues in the next session.